Okay, right after the introduction, let's go ahead and talk about the different tests one by one. Let's start with the one sample test. Okay, so one sample test is used to compare the sample mean, the mean of the group, to a hypothesized mean. And the Z equation that you see on the right is basically what you do in one sample test. You calculate a Z score to tell you how confident you are to reject your null of status quo, right? And in order to do that, you take your sample mean, you subtract the hypothesized mean from it, and then you divide the whole thing by the standard error of the mean. So the standard error of the mean is just a little parenthesis to explain you what is going on. It is the standard deviation. It is the closest thing that we can calculate to have the standard deviation of the population. So we're trying to take into account the standard error of the population. This is the population distribution. This is the sample distribution. I drew it a little bit bad, but it's supposed to really be something like this because the mean is supposed to be equal across the two distributions, right? So this is your sample. And the standard error is actually, so this is SX bar, the standard error is actually the hypothesized standard deviation of a bunch of samples means that are plotted up on a distribution. It's called the sampling distribution. Sampling distribution is a distribution of multiple samples plotted together, all right? Means of different samples, means of many samples plotted together. And this is actually only one, so let's erase the rest and leave only one curve right there, and that's the one curve you have as the sample distribution, right? Okay, so this is a distribution of different samples. This is your population distribution. This is your sample distribution. And what you have as tangible distribution in front of you is only this, right? What we can see and plot is really this on SPSS. So these are all like basically fairyland world. It's theoretical. It's all intangible. But standard error is basically the standard deviation of this sampling distribution. That's what I wanted to tell you. And this is all in parentheses, so you're not going to be responsible on the exam for this. You may actually know it already from your statistics classes. And so the Z formula is as follows. X bar, your sample mean minus hypothesized mean, divided by SX bar. Okay, let's go ahead and now do an example together. So the example is as follows. A researcher proposes that if a product package is red, attitudes towards the product will be positive. Hence, he decides to conduct a test across one group. He packages some products with his proposed red dominant packaging and surveys 164 people about the red package. He calculates that people respond 4.5 on an interval scale of 1 to 5 about how much they like the product, which is basically the mean of 164 people, right? With a standard deviation of 0.5. Are the attitudes toward the red package significantly different than the midpoint of the scale, which is, neutral from 1 to 5? How do you feel towards this packaging? If the person picked 3, it's the midpoint of the scale, And in other words, the consumer is neutral about the packaging. Run an analysis at the 0.05 level of significance. So first of all, let's talk about our null and our alternative hypotheses. So our null hypothesis is that in one sample tests, your null hypothesis is always H0 is mu is equal to the hypothesized mu or test value. So in this case, our null hypothesis is that mu is equal to 3, right? And then your alternative is that mu is not equal to mu h in one sample tests. So in this case, our alternative is that mu does not equal 3. As I said, in research, we usually want to prove the null wrong. We want to reject the null. So let's go ahead and calculate this z-score right now, z-test score, to see what we can conclude about this question. So it's x bar minus mu hypothesized divided by s x bar, right? What is your x bar? Well, the guy ran something something, and 164 people said that on average 4.5, right? It's right here. People respond 4.5 on average. What is the hypothesized test value? 3. We're trying to see if 4.5 is statistically significantly different than 3. Then the equation for Sx bar is S divided by root n. S in this case is 0.5. It's the standard deviation of the sample. It's right here, standard deviation of 0.5. And then n is square root 164. So we put that right there, 0.5 divided by 164. And then we have to solve for this. 4.5 minus 3 is 1.5. And then we have this number equaling 0.039. I did that on the calculator. And then that equals 38.4. So what happens now? What we see is that we got an observed z-value, z-test value of 38.4 without me saying anything about the critical z or etc. Let me show you on a z world where 38.4 lies. As you guys will remember, the z-scores are distributed on the standard normal curve, and the mean z is 0, and then we all know that 68% of the data lies within one standard deviations from the mean, yada yada, remember? And then 95% of the data approximately lies within 2 standard deviations of the data. 99% approximately lies, -3, lies within 3 standard deviations of the data. So obtaining a z-test value, which is very similar to the idea of having a z-score. They're different. Z-scores basically tell me how many standard deviations a score is away from the mean. But z-test values do have the same logic of probability analysis. And if I get a z-test value of 38, then I can figure out that it is a very, 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 very low probability that I randomly found 4.5 among my sample in terms of their responses. So the two means, 4.5 and 3, are 38 standard deviations away from each other, and that means they're pretty away from each other. They're statistically significantly different from each other because on the z-score, 38 is like way on the very right of the z-score distribution, and that means getting a z-test value of 38 is a very small chance. Because it's a very small chance, we feel confident enough to reject the null. So when we get a z observed that is larger than, in absolute value terms, than the critical z, we reject the null. What was our null? It's that mu is equal to 3, right? So when we reject the null, we can say that mu does not equal 3. And that means that the sample mean of 4.5 is statistically significantly different than the midpoint of the scale, than 3. We therefore infer about the population mean that the population mean is statistically significantly than the midpoint of the scale. Well, therefore, we can say that people react statistically significantly different for red packages than neutral. And this is a two-tailed test. Therefore, I actually technically, until I look at which one is bigger, is the sample mean or the hypothesized mean bigger, we have to look at them. Mu hypothesized was 3, sample mean was 4.5. So I can say that, oh, because sample mean is equal to 4.5, I can conclude that that's definitely a conclude. Consumers evaluate red packages more positively than neutral. I may ask you in the exam a question along the lines of this example, and I may ask you guys to tell me whether you reject the null or not, what your z value is, z observed test value is, etc. But, and I will always give you the z critical, so this is a 0.05 level of significance, so you know that 95% confidence interval is always associated with a z critical score of 1.96. And then, as you will recall, the 0.01 confidence interval, which is 99% confidence interval, is associated with the z critical score of 2.58. I'll give you that those two numbers in every question. But I will actually also talk about a couple of other methods that we could come to this conclusion, one being the p-value and the other one being the confidence interval approach. And I will talk about those two approaches for your information only. The p-value approach is going to be very useful when we are running SPSS analyses. So you have to know how to interpret any output from SPSS, and you will use that method when we're looking at SPSS output. However, I will not ask you in an exam how to run the p-value approach or the confidence interval approach in an exam setting. So these are all FYI only, the next couple of slides. And I will actually record these in another video. I highly suggest that you pay attention and learn what these are. But this initial approach, the critical z-value approach, is going to be the one and the only one for one sample tests if I ask you to hand crank a one sample test in the exam.